Okay, so last class on Friday, we talked about, got a lot of stuff there. We talked about designing our own circuits using sequential logic. And what we found was that we could basically take whatever our current state was and our input and figure out what our next state and our output was going to be. And at that point, we have effectively a truth table scenario where we can reduce, come up with some flip-flop input equations. This is what we came up with last class. Okay, so today, I'd like to go back a bit if we can. I'm going to put a D flip-flop up on the board here. Like so. And I'm going to design a circuit. Relatively simple here. 2 AND gates and an OR gate. That'll come from there. Give an input there. This will have an inverter on it. Give it some name. That. And remember, this is Q, and this is Q bar. So today I'd like to start. Let's analyze this. Can someone give me the input equation, the flip-flop input equation right there for this simple circuit? This is a circuit with 2 inputs. They're called J and K. A single out. See, now you guys have got me doing it. Look what I did. Look what I did. Q naught. This is why you can never ever say Q naught, because you'll just confuse the poor professor right out of his mind. Q naught. It's all your fault. I remember on Friday there were like 3 of you. And Abe isn't even here for me to yell at him. It was his fault. I'll blame it on him. So what is this input equation here? D is going to be equal to what? Well, something ORed with something. I can tell that because of the OR gate there. Looks like J ANDed with, then we trace it along, Q naught, K naught, ANDed with Q. Okay, so that is our flip-flop input equation. Now, we can go through and we can figure out a truth table for this. Wouldn't be too hard. Let's do that right now. For J and K as inputs, what will we get? And here I'm going to introduce this a little bit. The idea that we're solving for the input equation D. Yes, it is. It's because I can't write. It is ANDed. That's an AND gate. Sorry, when things are in parentheses, I just tend to kind of go OR. So that's great. That's J, Q bar, OR, K bar, Q. This sort of looks like an exclusive OR type sort of situation. At least when I look at it, I think that. So let's take a look. When J and K are both zeros, let's take a look. What happens? That's a 0. So 0 ORed with anything, 0 ANDed with anything is what? It's 0. And then K is 0, which means the input to the AND gate is a 1. 1 ANDed with anything is just that anything, so this is Q. So 0 and Q is, it's just Q. All right, let's do it again. Reevaluate here. We do 0, 1. 0 and 1. What'll that be? So 0 ANDed with anything is again 0. 1 becomes a 0. 0 ANDed with anything is 0. 0 or 0 is 0. So again, this is Q. So then we continue on. 1, 0. All right, let's redo that here. what do we have? Let's do some little analysis here. Okay, 1, 0. So 1 ANDed with anything is just itself, so that's Q bar. 1 ANDed with anything is itself, so that's Q. What is Q or Q bar? This is one of our fundamental theorems. Yes? It's 1, right? Think about it in the two cases, right? If Q is 0, that's 0 ORed with 1. If Q is 1, that's 1 ORed with 0. In either case, doesn't matter. It's 1. So there we go, 1. And finally, yep, let's look through this again. Finally, we go 1, 1. So that 1 becomes a 0 there. 1 ANDed with anything is itself, so there's Q bar. 0 ANDed with anything is 0. What is Q bar ORed with 0? It's Q bar. So 1, 1 is Q bar. And we can actually simulate that. Let's just do that because we like simulating. Here is my circuit. There it is. I've got my clock set up in the middle here. And you can see right now, if I'm toggling my clock, every time I go to a rising edge, we actually get Q become whatever Q wasn't. It toggles it because my inputs are both 1. So as I go through this, this will toggle forever. Every rising edge, it toggles. If I put them both at 0, as I toggle this, I can toggle this as much as I want. Q stays whatever Q was. If I set J to a 1, in this case, nothing happened, okay, because we were already in the state we were going to end up in. We were already in Q equal to 1. If I instead set K high, and I toggle it on the rising edge, I set Q to 0. This particular setup is actually really cool. It's so cool that it has its own flip-flop type. Okay, this is called the JK flip-flop. Ignore the fact that there are bubbles here. I don't agree with how they're setting this up on every circuit. But we can see the same stuff. Here I have them both as 1s, and as I toggle the clock, I can see that my output Q is toggling. So one of the things that I want to talk about now, typically we'll talk about Q and Q. When I talk about Q as an input equation, I'm really referring to Q at the current time, and I'm going to be solving for Q at T plus 1, meaning after the clock edge. Just a little bit of mathematical notation so we don't start confusing our Q's. Okay? So when I say Q of T, that means whatever Q is right now. When I say Q of T plus 1, that's 1 clock cycle later. Let's look at another setup here. This one's even simpler. D flip-flop. D. Bar has one input T. So let's take a look at T. Because the input equation is just dead simple. D equals T exclusive or Q. Now this Q that I'm talking about is Q at time T. And D is really Q at T plus 1. That's what we're solving for. We're saying, what will it be next cycle? Well, let's take a look, right? Let's write up the rules that we know about exclusive OR. X exclusive OR 0 is equal to something. X exclusive OR 1 is also equal to something. What is anything exclusive ORed with 0? Let's put up the truth table. AB 0, 0, 0, 1, 1, 0, 1, 1. XOR. That's a 0, 1, 1, 0. So if I exclusive OR with a 0, 0 becomes a 0, 1 becomes a 1. That's just X. If I exclusive OR with a 1, 0 becomes 1, 1 becomes 0. That's X bar. So when I come up with my table here, T, if T is 0 or T is 1, Q at time T plus 1, if it's 0, it'll just be whatever Q was at time T. And if it's 1, it'll be whatever Q bar wasn't. It'll be the opposite of Q of T. And this one is called a T flip-flop, or T stands for toggle. So the idea is you can toggle. Now, designing things using these higher order flip-flops, it's all based around a D flip-flop, right? But designing with these things gets a little bit more interesting. And let's talk about that. So to talk about this, when we did our design last class, this is what we had, right? If this was our inputs, that's what our new outputs were. And we just took this whole table and we shoved it into that K-map. Okay. So we need to have a talk about two new types of tables. We've used them without really knowing what they are. First off, we're going to talk about characteristic tables. And I can't spell it. C-H-A-R-A. Stop showing off a characteristic table. Just because you can spell, you were late, so you didn't hear me berating you for last class. Oh yeah, I wrote Q coming out of a D flip-flop, Q and Q. Oh no, I did it correctly that time. What did I write? I wrote Q and Q naught, which is not correct. Q naught is supposed to be Q naught. And it's because somebody, and I'm not going to name names here, but somebody was filling my head with nonsense on Friday. Okay, characteristic tables. What's that all about? A characteristic table, characteristic table says, for a given input, what will Q of T plus 1 be? So blah, 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 blah. Compares input to the next output. We're also going to talk about excitation tables. Excitation tables are a little different. They say if you know where you are and you know where you want to go to, put these inputs in. So if you know where you want to go from where you are, put inputs in. Let's look at these tables, okay? So for characteristic tables, those are the easiest ones to understand. And let's put up the characteristic tables of the three types of flip-flops we know about. D flip-flops, and D is our input, 0, 1, and Q sub T plus 1 is our output. So if you put a 0 into a D flip-flop, what will you get the next cycle? This is the easy one. If you put a 0 in, you get a 0 out. If you put a 1 in, you get a 1 out. It really doesn't get much more complicated than that. T flip-flops are a little bit different. So if you put a 0 in to a T flip-flop, next cycle you're going to get whatever you had. It's effectively a hold. If you put a 1 in, you're going to toggle. JKs are the tough one. Because JKs, have more states. If you put in a 0, 0, that is a hold state. If you put in a 0, 1, that will give you a fixed 0. It's not related to what has happened in the past. You put in a 1, 0, that gives you a 1. And if you put in a 1, 1, excuse me, I don't know why I put that bar there. That doesn't belong there. Overzealous writing. Q of T bar. So that is characteristic tables. Gives you the characteristics. For a given set of inputs, what will happen? And the nice thing about characteristic tables is it doesn't seek to give us absolute zeros or ones. It just says, all right, it's going to be whatever it was in the past, or it'll be whatever it was in the past's opposite value. And so you can start to see that D is kind of the dumb one. It doesn't rely on past state. It only relies on what the input is. So it's the easiest one to start designing with because we can just take whatever our required output is, throw it out there. Excitation tables get a little bit more complicated. Let's talk about the excitation tables. So, excitation tables always as your input have Q of T and Q of T plus 1. And what they have as a result is what you need to provide on the outputs. So let's say that we're in state 0 and we want to go to 0. Or in state 0, we want to go to 1. In state 1, we want to go to 0. Or in state 1 and we want to stay in state 1. What do we need to put on the input for a D flip-flop? And D is kind of the counterintuitive one. We haven't talked about excitation tables yet because they're so mind-numbingly counterintuitive. Here's the excitation table. Okay? It doesn't matter. This column just does not matter. The only thing that matters is where you want to go for a D flip-flop. T flip-flops get a little bit more interesting. Okay? Let's do a T flip-flop. Let's first start off with the characteristic table for a T flip-flop. Okay, sorry, Q of T, Q of T. There's the characteristic. Now we have to fill in the excitation table. We're going to derive it. So if we know where we are and we know where we want to go, what do we put on T to get there? So this is an interesting question. If we are in state 0 and we want to end up at state 0, what do? Well, what we can do is we can go over here and fill in values. So if we know that Q of T is 0, then we can fill this table in as follows. If you put a 0 into T, you'll get whatever Q of T was, so that's 0. If you put in a 1, you'll get a 1. That's if you are in a 0 state. So the answer here is to get from 0 to 0, you put in a 0. To get from a 0 to a 1, well, the input hasn't changed, so what do I need to put in as a T to get to a 1 from 0? Well, if I put in a 0 and Q of T is a 0, I'll get a 0 out, so that's not going to work. If I put a 1 in, it'll give me the opposite of whatever Q of T is, and Q of T is 0. So that'll give me a 1. Now the input changes, so no longer does this truth table apply. It's actually reversed now. Q of T is 1. Q of T bar is 0. So if I'm in state 1 and I want to get to a 0, that means now I need to put in a 1. And if I'm in state 1 and I want to stay as a 1, I need to put in a 0. This looks very similar to an exclusive OR, because it is, right? That's how we built a T flip-flop. So that's the characteristic table. All you do is you look at how can I get to my desired output from my current output if these are my choices. Now, JKs are the toughest ones to derive. Okay, let's start with the characteristic table for a JK. Inputs on the left, Q of T plus 1 on the right. 0, 0, 0, 1, 1, 0, 1, 1. And we have seen now that it's Q, 0, 1, Q bar. And these are obviously of T. Okay, so deriving the excitation table says, all right, if we are here and we want to go there, what do we need to put on J and K? This is a mandatory participation part of the course. So if I want to get to a 0, what can I put on J and K to make Q of T plus 1 a 0? Look at the table. What? Say 1. Well, there's 2 inputs, so give me both J and K. What do J and K have to be to make the output 0? Right, and you look right there. There it is. It's 0. Absolutely. That's not the answer. It's part of the answer. Are there any other ways? If we know that we're here and we want to stay here, are there any other rows that will let us stay or hold our value? 0, 0 will also allow us to get a 0 if we're already in state 0. So if we're in state 0, setting both of our inputs low, we'll stay in 0. Now, what does this mean for us? This means that our excitation table now says we must have a 0 for J, but K can be either 0 or 1. So it's a don't care. Don't cares always lead to simpler implementations. Let's take a look now. If we're in state 0 and we want to go to 1, well, I'm going to give it to you now. I know that putting in for J and K, putting in a 1, 0 will definitely give me a 1. That sort of looks like a T. Let's make that a J. What other row in this truth table will change a 0 to a 1? All right, going from a 0 to a 1 is toggling. So what inputs on J and K will cause the output to toggle? In the back. 1, 1. 1, 1 will give us whatever Q was, but the opposite of it. So that means, so what is my entry in my excitation table? Remember, this is characteristic. This is excitation. What will my entry be? If these 2 values will both satisfy the requirements of going from 0 to a 1, it's going to be a 1, don't care, because K, again, doesn't really matter. Okay. Now I'm going to use a different color just to kind of keep us on the straight now. So now if we're in state 1 and we want to go to state 0, well, first off, I know that we can toggle because it's toggling. The other option is we can just set it directly to a 0. That's a 0, 1. So since both of these are 1, I know my answer is going to be 1. Since this is either or, that's going to be a don't care. So I have don't care, 1. Finally, going from a 1 to a 1, first off, I can set it to be a 1. So that's a 1, 0. Or I can hold, which would be a 0, 0. In this case, both of these are zeros, and this is don't care, so that's a don't care. So it's don't care, 0. You'll see that there's kind of a crisscross pattern here. Don't cares, and then 0, 1, 0, 1, or sorry, 0, 1, 1, 0. Typically, I never remember this table. I know that that's silly to say, right? I've been doing this for many years. I never remember this table. All I do, however, is derive the first one. Then I know where the 0 is and where the x is. So once I know that that's 0 and that's x, I know the next x goes there, that x goes there, that x goes there. And if that's a 0, then that's a 1, 1, 0. That's how I remember it. That doesn't have to be how you remember it. You can put some flashcards together. You can always derive it, though, from the characteristic table. Because I do remember the characteristic table. And the reason I remember this is because we've seen something very similar to this characteristic table before in a latch. What latch? What latch has a hold and a 0 and a 1 state? It's the only latch, actually, that has 2 inputs. Yeah, an SR latch. Right? When we put in a 0, 0 to an SR latch, that was its hold state. When we put a 1 into the reset, and this is sort of how it looks, right? S and R. K is kind of like your R. When we put a 1 on R, that reset the output. When we put a 1 on the set, it set the output. The only difference here now is this state right here. This wasn't part of an SR latch, right? This had some problems with it. It was its forbidden state because it caused astable operation. So we've got these excitation tables. All right. So what we're going to do now is we're going to redo our implementation from last class. All right. We had, let's go all the way back now. We had this. This is what we had here. All right. And I'm going to grab it. I'll grab the whole thing. We knew that this is what we needed to create. Okay. Now, the reason we were able to do this is because of the excitation table for a D flip-flop. A D flip-flop says that if you want a 0, okay, if you want the, whoa, stop that. If you want a 0, all you need to do is put a 0 on D. But if we're working with any of these other flip-flops, it gets a little more complicated. Here's how we do it in the case of a JK flip-flop, which is the harder of the two to write down. All right, I'm actually going to change my background here now that I'm thinking of it. To do this correctly, all right, I'm going to, actually, let's do this. I'm going to rewrite this whole thing over here. I'm just going to use this as my notes. X, Q1, Q0. Now, these are Q1 and Q0 at time t. That leads us to Q1 and Q0. These are the ones that are at t plus 1. These are the ones at time t. So here we go. 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. And now I put in Q of 1. 0, 0, 0, 1, 0, 1, 0, 1, and Q0, 0, 0, 1, 1, 1, 1. No. Whoa, 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 whoa. Back up. Slow your roll there, Professor. 0, 0, 1, 1, 1, 1. There we go. Okay. So here's my at time t. There's my at time t0. From here, building your circuit takes a bit of a left turn. I'm going to redo my excitation table. Right there. There's my excitation table for a JK flip-flop. You'll sometimes see this notation, little q, big Q. Typically implies that there's a change in time. All right. In my case, it was just that I couldn't write Q of t plus 1 in these nice squares. Here's how we're going to do this. First thing we're going to do, I'm going to circle the two things that say Q sub 1. Really, I guess I'm boxing them, not really circling them. Now, this is Q of T, and this is Q of T plus 1. What I'm going to do now is I'm going to add to this table. I'm going to add in a J1 and a K1. And all I'm going to do is reference this table over and over and over again. So I'm going to look. I see here that I'm going from a 0 to a 0. So I reference 0 to 0. That's a 0, don't care. I'm going to do that the whole time. 0 to 0 is a 0, don't care. 1 to a 0 is a don't care 1. I'm going to take this time to erase this line because it is confusing me. This is the kind of problem where keeping yourself neat and tidy is really going to be the difference between getting the right answer and the wrong answer. If you are not looking at the correct columns, it's going to cause you a problem. So here I've got a 1 to a 1, don't care 0. 0 to a 0 is a 0, don't care. 0 to a 1 is a 1, don't care. What's a 1 to a 0? Don't care 1. 1 to a 1, don't care 0. Now that I've done that, I'm only half done. I now need to do it for Q0. So I'm going to put in J0 and K0. You guys are going to do this one. See if you can check this column against this column and come up with some numbers for J0 and K0. I'm going to show you why this is so, it's worth going through this extra effort. It really is, in terms of your implementation details. So take, I don't know, a minute and fill this in. All right, so what do we have here now? Let's do the first one here. 0 to a 0 is a 0, don't care. Somebody just start reading it off to me. 1 to a 0. 0 to a 0. 1 to a 0. 0 to a 1. 1 and don't care. 1 to a 1. 0 to a 1. That's correct. 1, don't care. A little confusion there. 1 to a 1. Don't care and 0. So overall, this process, not that much more work, does require a little bit of extra care in terms of lining things up, but it's really just referencing this table over and over and over again. What do we get for all of this? Well, first off, we get more work because unlike last time, when we did this last time, we only had a K-map for Q1, a K-map for Q0. Now we have 4 K-maps, 2 per item. So now I've got to do this, and I might even be able to do it like this. Hey, I like this graph paper version. That's pretty swanky. I'm almost drawing straight lines. Is this helping, by the way, using this kind of paper for you guys? faster? Okay. So here, I'm still going to use the same ordering, X, Q1, Q0. Okay, and that's dictated by the way I listed it off over here. And it's going to be important that I still pay attention to my gray code and so forth. X, Q10, 0, 0, 0, 1, 1, 1, 1, 0. So let's call both of these J, both of these K. This will be sub 1, this will be sub 0. Everybody understand how I've labeled this? All right, so as I read across this, this is going to be J1. So it's, do it in red, 0, 0, don't care, don't care. 0, 1, don't care, don't care. As I do K, that'll be don't care, 1, 0. Don't care, 1, 0. For the J0, that'll be 0, don't care, 0, don't care. 1, don't care, 1, don't care. For the K, that'll be don't care, 1, don't care, 1, don't care, 0, don't care, 0. Okay, so first off, we see that we have a lot of don't care conditions, which is nice. When we simplify this, looking along here, somebody catch me if I make a mistake here. We've got a cell there. We've got a group of 4 there. Here I've got a group of 4 there. And finally a group of 4 there. So what do we end up with? 0, 0, 1, 0. That looks like Q0 bar. So that's K1 is equal to Q0 bar. K0 is equal to X bar. J0 is equal to X. And J1, gosh, I wish it was something a little nicer. I guess it's equal to X ANDed with Q0. Let's just check. Any chance I made a mistake here? 0, 0. Don't care, 0, 1. No, I guess that's as good as we can do. What that means, though, and let's just do a direct comparison here. Our circuit is still going to be 2 flip-flops. J, K, clock. J, K, clock. Q1, Q0. The difference now is in what we have to do. So this is J0, K0, K1, J1. Hooking up K0 is as simple as going X bar. J0 is X. K1 is Q0 bar. And J1, that's the only input that actually requires any gates. X, Q0. Obviously, this is a sequential circuit, so we will have that clock line connected in, but that's sort of beside the point. We care about the logical function of the inputs. So designing with these, not too bad. The only thing we have to do is add on or augment our transition table with our flip-flop input equations. Okay? To do that, all we're doing is referencing our excitation tables. To build our excitation tables, we reference our characteristic tables. And our characteristic tables are really just how the circuit functions. So let's go back. Let's do a review here of what we've done. We started with 2 things, characteristic table and an excitation table. We defined a JK flip-flop like this. Okay? Have to remember how to build a JK flip-flop or know where to look it up. We defined a T flip-flop as an exclusive OR gate. In both cases, these JK and T flip-flops have some kind of feedback from the output of a D flip-flop. They're all based off of D flip-flops. Okay? So our characteristic table says, for a given set of inputs, where will we end up? our excitation table says, if we know where we want to end up and where we are, this is what you put in to get there. Here are our characteristic equations for all three flip-flop types that we've discussed so far. Then we went ahead and said, all right, the excitation table for a D flip-flop is kind of boring because it doesn't really care about this part. The T flip-flop was a little more interesting because we have to rely on our previous state. We cannot set things to 0 or 1. We have to know where we were, and then we can set things. Finally, our JK flip-flop gives us the flexibility to do either. We can either, as in the case of the middle two, set them high or low, set the output high or low. Or in the case of the upper and lower, we can rely by holding or toggling. The only change is now our implementation takes one more step. We still do everything the same way we did last class, but once we've got what we want our outputs to be, then we add on, based on the excitation table, more rows. Not shown here, by the way, was the Y output. Our combinational output does not apply. Okay. Oof. Not too bad. Questions on that? All right, we have one more thing that I want to talk about. And we'll be using it later. Come on, new page. Really thinking about it. Let's say that we're designing some kind of a washing machine or something, and we find that we've got something like this. State A goes to state B if the input is 1, stays in state A if the input is 0. B goes to C if the input is 0, stays in state B if the input is 1. C goes to A if the input is 1, or back to B if the input is 0. That's our state diagram. I have completely pulled this out of thin air. Okay, so if we're going through our design process, this is our design. Maybe we minimize states, maybe we don't. Maybe this is as a result of our minimized states. I haven't really checked if we... Yeah, this is not going to be minimized any further, I don't think. Yeah, okay, so that's pretty good. So let's build up our state transition table. All right, we've got current and next. Current includes not only our states Q, but also our input X. And how many bits of Q do we need? How many bits of state? Well, how many total states do we have? 3. How many bits do you need to represent 3 states? Let's start counting them off. State 0, state 1, that's 2 states. To represent the last state, we would need to go 1, 0. So in total, we need 2 bits. So that's Q0, Q1, and X. So let's look through that now. 0, 0, 0, 0, 1, 1, 1, 1. And our Q0, that'll be 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. We've got to assign some names to this. So let's say that state A is 0, state B is 1, state 2 is 2, or state C is 2. So in A, if X is 0, we stay in A, which means we go to 0, 0. If A is 1, we go to B, which is state 0, 1. If we're in state B and we have a 1, we stay in state B, 0, 1. Otherwise, we go to state C, which is 1, 0. If we're in state 2 and we have a 0, that goes back to B, that's 0, 1. And if we have a 1, we go to state 0, 0. And if we're in state 3, hang on, whoa. Where is state 3? We've got state 0, 0, state 0, 1, state 1, 0. Where's state 1, 1? Yeah, of course, it's not there. That indignation was perfect. It's not there. You don't have one. And that's exactly right. So this is the trick, right? We don't have one. So what do we do? What do we fill in here? Well, the answer is, if that state doesn't exist, if we can, and this is the trick here, if we can never get to that state, well, then we don't care where we go. It doesn't matter where we go. This does, however, bring up a problem. So we have this thing, and let's say we're implementing with JK flip-flops. So we have to augment this now with J1, K1, J2, K2. We look at our excitation table, Q, capital Q, and J and K, 0, 0, 0, 1, 1, 0, 1, 1, 0, don't care, 1, don't care, 1, don't care, 0. And we look, and every time we just look, okay, this is 0 to a 0, that's a 0, don't care. This is a 0 to a 1, that's a 1, don't care. This is a 1 to a 0, that's a don't care 1. And this is a 1 to an X, which is not in my table. Well, what do I do now? X isn't an option in my table. Well, let's think about that. If we don't care where we're going, does it really matter what my J and K inputs are? No, it doesn't. J and K control what my output will be, but I don't care what my output will be, so I don't care what either input is. And this is the crux of the matter right here. If you have what's called an unused state, then the answer is we don't care. All right, let me quickly fill in this table because there's one sort of gotcha here, all right? So 0 to a 0 is a 0, don't care. A 0 to a 0, 0, don't care. A 1 to a 0 is a don't care 1, and that's don't care, don't care. When we simplify this, I'm just going to do, actually, I'll do both pretty quick. I'll do both quickly here. Boom, 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 boom. 0, 1, don't care, don't care. 0, 0, don't care, don't care. What are we left with? Looks like X bar with Q0, and this is going to be, where are we here? Don't care, 1, don't care, 1, don't care. What does this reduce to? Can I grab that group of 2, or should I grab a group of 4? Yeah, you can grab the whole group of 8. We don't see that very often, but with JKs, it's actually more common. So that's J1. K1 is just equal to true. So when we build this, flip-flop J, K, all we're going to do is tie this guy high, and we'll tie this, to those two things. Now, here's the deal. Once you've simplified this, they stop being don't cares, all right? I'm going to redo J1. If I'm only looking at this equation, what will I get? So J1, and I know I'm kind of crowding things on here, J1 is going to be X bar ended with Q0. So that's going to be 0, 1, 0, 1, 0, 0, 0, 0. You can check that out a little bit later. I know we're running short on time. What we've seen now, however, is this don't care suddenly becomes a 1 because that's how we implemented it. And of course, that's what it's going to be because we circled it. Okay? And likewise, the K will also be a 1 because we circled it. So when we are in state 3, we're actually going to find that the Q1 input will go from state 3, and we know that it will go to state 0. We didn't do the lower bit here, Q0, J0 and K0. But we know that it will go to some finite state, either 0, 0 or 0, 1. We could go through if we had more time and do that. Here's the thing, though. If we found, because state 3 is going to exist, if we found that state 3 actually stayed in state 3, that would be a big problem. Because just like we saw many times with our latches, on startup, they can be in kind of an undetermined state. If your flip-flops come up in an undetermined state, then you might start in state 3. And if state 3 loops on itself, you'll just stay in this loop forever, which is bad because you want to be here. This is sort of your known stuff. Here there be dragons. So you don't want to be there. So there's one vocab word I want to run across to you. No, not forever. That's not the vocab word. It's new page. New page is the vocab word. Come on. Self-starting. Self-starting means that if you've got some known setup here, and then you've got some unused states, so this is used, this is unused, a circuit is considered self-starting. Doesn't matter how many states are over here, as long as there is one transition, at least one, transition from unused states with an S, to used states. So, generally we want to design our circuits to be self-starting. This is part of our verification phase, phase 8 of our design process. We have to go back and look and see, are any of our states, our unused states, caught in a loop? So for example, this red, it takes a couple of clock cycles, but does eventually get back to a into a used state. If instead we saw that it only in blue here went like that, and then around, if it stayed in here and did not have a connection to used states, that's what we would call not self-starting, which is a problem. Okay, so sometimes, even though you have a really nice solution, like we got to select all of these X's, sometimes you have to go back and actually use a suboptimal implementation to make your circuit self-starting. All right, we'll be doing more with don't cares next class. How are we due? Are we due for an exam anytime soon? April 28th? Okay, so we got a little while. But homework chapter 5 was assigned, in case you missed it. Homework chapter 5 up on the board. Other than that, class dismissed.